Welcome to this webinar titled Expect the Unexpected. I'm Simon Brittle, Assistant Chief Engineer at Rolls-Royce, and today I'm presenting on behalf of the Structural Technology and Materials Group at the IMechE, and that's a group made up of cross-industry people with an interest in structural integrity issues across a fairly broad industry range. The purpose of this presentation is to share experience. I've been working in the nuclear industry for about 32 years in a variety of technical roles, sometimes on site with a spanner in my hands, sometimes leading technical projects, and my more recent roles have been in senior leadership in both operations and customer-facing spheres. And the thing that I have observed over those 3 decades is that the unexpected can and will happen. We make the best plans we can, but sometimes things happen that we don't expect, and the consequences can be quite significant. They can lead to safety concerns or loss of availability of our products, or they can simply be reputational or cost us money, time and resources to fix. So obviously we want to avoid those consequences, and hence sharing experience in a fairly broad sense so that it's transferable across to a range of industries. The main focus today is not on discrete case studies, but on the broad learning that I've picked up from observing a significant number of events over the years. And I'm really going to focus on how communication and delivery of requirements is essential. The opportunities for risk and for things going wrong often exist in that communication between different functions or the physical delivery of the hardware. And I think that learning can be applied to pretty much any sector of engineering, particularly critical to high integrity sorts of fields. So if I just explain briefly what I mean by high integrity, those that work in the nuclear sector will recognise that term. We safety classify components according to the consequences of failure of those components and systems. So we have safety critical, high integrity, very high integrity, incredibility of failure as terms that we're familiar with in nuclear. For the purposes of today, I'm just describing systems that we need to rely on for safety and reliability as being high integrity. And that again can be read across to oil and gas, chemical processing and other relevant industries. Where we have a high demand on the reliability of a high integrity system, then this topic of structural integrity becomes fundamental. And for me it's a very holistic concept. Structural integrity is a combination of good design, good quality control in the supply chain, good quality in manufacturing, good understanding of operational conditions, good analysis that demonstrates that we've got margins against failure through all of the boundary conditions, loading conditions that the part will see in service. So it's a very broad topic. Rather than try to bite all of that off in one fairly short webinar, I'm going to focus today on some discrete areas where things can go wrong, and I'm not going to delve into analysis methods, codes or standards. But please do watch out for events later this year. Probably in October, the SGMG will be holding an event on the design substantiation of high integrity parts, which I think will be a full day event and go into a lot more detail. So if you're interested in what we're talking about today, then please look out for that, because that should be a really good follow-on. I have tried to structure this webinar around 5 topics. So the first is material processing, and I guess we all know that you know, the material is at the heart of what we do. If the material is sound and meets the specifications that we have selected for the application, then that's a really good starting point. However, material processing is quite a difficult topic, and I've picked on heat treatment for this example because there's a lot that can go wrong, but there's a lot that we can do to reduce risk. So the example I've picked is forged bar. We use it for lots of applications, including threaded fasteners. And threaded fasteners are interesting because they usually see high loadings and high stress concentrations. So we want to make sure that we've got threaded fasteners that are going to withstand those loadings, but are also going to be corrosion resistant and have good properties through life. And so we will, in selecting a material, we might specify a heat treatment to deliver a very discrete microstructure within a very tightly controlled range. We'll be very clear on the composition, and we'll expect mechanical properties that we can rely on to feed into our analysis. Usually that means we've got to be quite careful about how we control the ramp up and ramp down of temperature in a furnace, and how long we maintain the heat treatment temperature. And then at the end of a heat treatment, we'll want to confirm properties. So we might go off and do quite detailed mechanical testing for a large forging, but for something like bar stock, where we're producing large quantities, typically we'll do quick and easy tests, such as hardness indents at the ends of a bar. And a hardness indent can be a good indication that the microstructure is acceptable. So here's an example of something that can go wrong. If you've got a temperature profile, and I've just shown it very clearly, very simply as temperature against time, that you write down in words in a specification, ramp up at this rate, hold for this period of time, ramp down at this rate, then you've got a requirement that's very simple and very clear, and if you apply it to a single bar, probably relatively easy to achieve. But if you go to a commercial supplier and ask them to heat treat large quantities of bar stock, they will understandably place as many bars as practicable in the furnace. So in this example, where the bars are tightly packed together, the outer bars will see the temperature profile shown, the ends of the bars will see that profile, but the inner bars and the central sections of the inner bars are shielded by the material around them, take longer to ramp up. They either might not reach the peak temperature required, or they might not stay at temperature for the required amount of time. And if your quality test is to hardness test the ends of the bars, that failure to get all of the material back up to the same temperature will not be revealed, because the ends of the bars will meet specification. So if you don't understand that and don't do something to manage it, structural integrity could be undermined. You could have significant variation in microstructure, significant variation in properties, and not achieve what the design has intended. So I think my key learning from having seen this sort of issue is that you can't rely on the specification alone to guarantee that the product will conform. It's really important that the designer and the materials engineers who will work closely with the designer spend a lot of effort to understand process limitations and understand how a supplier will try to deliver the specification that you've placed upon them. That close integration of the design and the materials engineer and the supplier to understand the process limitations will enable you to design the process to avoid those risks. So, for example, you could require the supplier to instrument up central bars with thermocouples. You could require that finished bars are cut into sections suitable for the intended final application, and the hardness checks are done not just at the bar ends but also through section at the centre of the bars. So there are lots of things you can do to manage the risk, but it relies on understanding the specifics and good cross-functional working. I thought it was worth sharing a good practice observation as well. So I've seen some very complex, very long lead, very high value structures made up of different materials with lots of transition welds, which require some sort of final heat treatment, usually because the complexity of manufacture leaves no option but to do a final heat treatment on one or another of different transition welds between dissimilar metals. And the risk there is that you can, in trying to achieve the correct microstructure for one transition weld or one material, you can undermine the microstructure and the properties of an adjacent feature, an adjacent transition weld perhaps. So that sort of very complex, very challenging heat treatment tends to get a lot of focus. We tend to put integrated project teams together. They work very closely. They design the heat treatment process very carefully. They use analytical modelling and FE analysis to predict what's going to happen to the component. And finally, I've seen pretty widely use of prototypic trials, which are expensive and time-consuming, but result in a very high level of confidence that when you go and press the button on the heat treatment for your complex high-value structure, that heat treatment is going to be successful. So I thought it was worth sharing that good learning, because for big complex items we tend to put a lot of focus in. For less complex items we perhaps relax a little, and what I'm saying is you should follow the same principle for both, but apply the appropriate level of effort. So that was my first topic. My second topic, and hopefully you'll see that there are some synergies between these. My second topic is inspection. So we can have great materials, but we need to demonstrate often that those materials are free of structurally significant defects. And by that I mean the sorts of defects that, although they might not be very likely to occur due to the good quality of the manufacturing processes we use, if they were to be present, would be structurally significant. They could result in a failure. So we often set inspection requirements to demonstrate that unlikely defects are not present, and that's over and above the standard manufacturing quality inspections that we're all used to. So in a forging or a weld, we might look for defects that we don't expect to be present, but that the safety case requires us to demonstrate are not there. Now, volumetric inspection techniques all have their limitations. So if you think about a weld, a radiographic inspection might be very good at finding a lack of fusion defect that is in the plane of the radiographic shot. Or it might be good at finding a volumetric defect such as porosity. But it might not be capable of detecting a stop-start defect in a plane that doesn't lend itself to radiography. So you might want to use ultrasonic NDE. So we often need to think about a combination of inspections, and in some cases, for the highest integrity parts, we have to formally qualify those inspections in accordance with various different codes and standards, which I won't go into today, but some of them require independent trials, blind trials where the operator is looking for defects hidden in a test piece and has to prove that they can find them and size them. Qualifying an inspection is expensive and time consuming, and it relies on a really clear definition of what the designer requires the inspectors to find. So I'm talking now about postulated defects and defects that would be structurally significant, and the designer being very clear about what it is they're looking for. So here's a simple example. Let's assume we've got two cylinders and they're welded together. How do we define very clearly, without ambiguity, what defect orientations we need to be able to detect in order to then pick the right techniques to guarantee that those defects are not present. So I've seen words written down, over the years, such as axial, radial, circumferential, well, they're good descriptors in relation to a feature like this. But just take axial for an example. In relation to the weld between the two parts, does axial mean the axis of the larger cylinder or the smaller one? Does it mean the axis of the weld, and what is the axis of the weld? So really what I'm pointing out is that words are vulnerable to misunderstanding. It's very easy when you write words down to know what you mean, but somebody else reading those words will put their interpretation on them. And this sort of very expensive NDE development that I've talked about, if we're not careful, can set off on the wrong basis, which clearly is going to cost time and cost money and end up in a result that's not usable. So my key learning here is to avoid confusion, use drawings as well as words. This is a very simplified illustration of that, but the red cylinder represents the weld. It's been labelled so that we know what's the axial direction, what's the radial direction, and what is the circumferential direction. And then you can, by illustrating the sorts of postulated defects that you want the NDE capability to be able to detect on the sketch or on the drawing, and putting some words around them, you can gain much better clarity. So if I said I'm interested in radial circumferential defects, okay, that perhaps helps because we can relate it to the sketch. If I say I'm interested in inter-run lack of fusion defects that are in the radial circumferential plane with a sketch, I've now given more detail, and somebody who understands how the weld beads have been laid down will really have good clarity on what I mean in specifying a defect of that type in that orientation. Likewise, if I say stop-start defect in the axial radial plane, an NDE engineer will look at that and say, okay, so I understand that the weld bead is laid down circumferentially. When you stop a weld and then start the next run, there's potentially an axial element to that, but it's also radial. I can see that on the drawing. That makes sense to me. So the important thing really is that NDE, is pretty invaluable, but you have to recognise NDE techniques have their limitations. NDE is not a panacea. It doesn't of itself mean that we've got good structural integrity unless you're absolutely confident in the technique. So it supplements good design and good quality control, but you must understand the capability and limitations of the NDE. And, more importantly, and this is under good practice observations now, designers and NDE engineers must work closely to confirm their understanding of both the capability of the technique and what it's being asked to achieve, and that requirements must be communicated without ambiguity. Going back to the example I gave on the last slide, always use drawings as well as words. If you just rely on words, there's a risk that there will be misinterpretation and you'll spend time and money developing a technique that doesn't answer the requirement that's been set. And at the end, when that technique is available, there's no substitute to the designer going and spending time with the NDE team, asking them to demonstrate the process, to confirm, by eyeballing what they're doing, that the requirements have been met. My third topic is a really simple one, and it's summarised on a single slide. And it's a topic that I certainly see time and again, and I'm sure many people do, and it's damage allowance. But I want to put it in the context of where we are today in terms of our design capability. So we have really advanced design and analysis methods and tools available to us today that mean we can optimise designs. So if you think of a pressure boundary part, perhaps a pressure vessel or some pipe work, we can, through good understanding of the loading conditions, very detailed finite element analysis, we can optimise the design to minimise that pressure boundary thickness, which will save us money. It'll save weight in the plant if that's important, and it'll save cost in terms of the volume of material that needs to be procured. However, mechanical damage is something that we see time and again. It can happen in a factory, it can happen on site during build and commissioning, it can happen in service and during maintenance periods. And if you're talking about very long lead, very high value items, then scrapping those items due to mechanical damage is not likely to be tolerable. But operating with mechanical damage in place is also not likely to be tolerable, and you've got to demonstrate that it's safe. So often, if there's a sharp feature that's been caused by damage, then you might dress that out to a smooth profile, but you're reducing the wall thickness. So if you don't have explicit margin in your design, then every time a unique case of damage occurs, perhaps close to a feature where there's a stress concentration, or in a relatively thin section, then you run the risk of having to either replace the part, which as I said is not very tolerable, or you need to do some individual assessment. And that might mean generating new FE models, running lengthy analysis, writing up a safety case, and that all costs time and money, and that can impact on reputation, it can impact on your finances, but it can also impact on the customer's ability to operate the plant in the meantime. So some good practice I've seen in the industry is when undertaking that design optimization process, add back on an appropriate damage allowance. Now this is a balance, it's a compromise, but if you know that accidental damage can occur, then accounting for it, although it might lead to slightly higher costs in manufacturing because you're putting a little bit back onto the pressure boundary thickness, it means that if it's explicitly explained on the drawing, any accidental damage that does occur that's within the limit that's shown on the drawing can simply be removed and blended to a smooth profile without further assessment. You're still compliant with the design intent. So overall, as an approach, applying an appropriate damage allowance on a drawing can save money and enhance your reputation. The fourth topic I wanted to cover is analytical conservatism, and to all my analytical and stress analyst colleagues, this really is not a pushback at use of analysis in any way. Analysis is absolutely vital to structural integrity. It's the prediction of reliability through well-tied and trusted and validated methods to give us really good confidence in the reliability margins that we have in our design. And I've said in my opening bullet, that calculated reliability margin should be against the predicted in-service loading and boundary conditions. However, that's where the problem can arise. So our guidance, for good reason, tends to be conservative. If we are feeding material properties into an analysis, we will tend to pick bounding properties, perhaps based on a statistical analysis of world data for the grade, or perhaps based on doing some discrete testing for the component itself, but we will always tend to a high confidence bound for the material properties that we use in the analysis. So that's conservative, and that's the right thing to do. We will then look at loading conditions, and again we will tend to be conservative. So we might look at a range of features across a component, try and understand which of those features sees the highest loading conditions, and then that's what we'll analyse as a bounding condition. But that means that we'll apply those high loads perhaps to other features, which could in later life mean that if we have a concern about those other features, our analysis has lower margins than it might otherwise have had, leading us to need to do more rework later. For components that operate in systems that see cyclic fatigue, we will probably predict a conservative cycle count, and we'll do that again for good reasons, because the plant might operate for longer than we originally thought. It might operate harder than we originally thought. Things can change. So it's good to build some margin in through having those conservative cycle counts. And then when we think about boundary conditions and heat transfer coefficients, we know that there are limitations to the tools available to us to CFD. We know that validation of CFD is sometimes challenging. Unless we spend a lot of money on running test rigs, then we'll probably pick conservative heat transfer coefficients at the boundary between metal and fluid. So, a lot of conservative inputs to our analysis. Some of our tools and design codes, however, also contain conservatisms, but those are generally less well quantified. It might be that a design code for fatigue is based on testing that was done 5 or 6 decades ago, and some margins were placed on the results and an uncertainty analysis undertaken, but that's not explicitly stated in the code. So the result of adding all of these conservatisms together can often be that a first pass analysis gives us an unacceptable result, and we need to then rework, remove some of the conservatisms to try and deliver an acceptable answer. Or we have to change the design. But my experience is frequently we've been able to get to an acceptable answer by removing known conservatisms. So I think my learning point is it's important to think carefully about what are the appropriate inputs to the analysis. I'm not saying that we should ever sacrifice safety or margin. I'm saying that we should put effort into better understanding it so that we better understand the answer that we get. And the seminar I mentioned earlier in October, the probabilistic versus deterministic seminar, will focus on some relatively recent thinking about how we might move forward to more of a target reliability approach to analysis. So perhaps slightly less conservative in the application of the analysis, but with better clarity of understanding what the true margins are likely to be. So I won't say more on this topic today, but I really would encourage people to look out for that seminar in October. My final topic, I did say I would try and just cover 5, is dimensional control. This might not seem as critical to structural integrity at first glance, but it really is important where we're relying on the function of a part to provide protection to an overall system. So good examples would be pressure relief valves, pumps, those sorts of components that have an impact on the structural integrity of the rest of the system, where you've got moving parts and where the reliability of that component to fulfill its function through life does have a reliance on achieving the tolerances that are specified in the design. Now, I've seen a number of examples over the years of where a tolerance on a drawing is related to the method of manufacture rather than to the functional requirement of the part. And an example of that is a part that was manufactured using a jig grinding process, where over many decades, and the part was very reliable, but over many decades the drawings had been amended and modified to make them easier to use by the manufacturer, and to reflect what the manufacturer needed to achieve at various stages to get a finally compliant part. So the design drawing became a manufacturing drawing that also recorded the design requirements. Now that's fine so long as your method of manufacture is stable, but I've seen an example where manufacturers have gone out of business, so there's an obsolescence issue now, no manufacturer available with equivalent capability, and so a new manufacturing process has to be developed for the part. That's a point at which real risk occurs, because if your drawing is full of very tight tolerances and you haven't explicitly stated which of them are critical to the correct function of the part, then in trying to chase compliance with all of those tight tolerances, you might inadvertently undermine the ones that are most important to function in order to achieve the ones that were only there as an aid to manufacture. So very important to spend time and effort understanding what's truly important to functional performance. And in the example I just mentioned a few minutes ago, we spent a lot of time and effort trying to re-establish our understanding of what was important to the design and what was important to manufacture. And in doing that, we were able to define then a new method of manufacture that delivered a part that looked different to the previous part, but was actually still acceptable. So I think another way of summarising that is that for a long-standing design that evolves over time, the explicit knowledge of what good looks like can be lost. So you need to explicitly document that somewhere, whether it's on the drawing or whether there's a design basis document that needs to be produced to sit alongside the drawing. It's really important that it's written down in very unambiguous terms. In the example I gave earlier, the way that we confirmed that we had re-established what good looks like was through undertaking functional testing. So we made new parts to a new method of manufacture. They looked different to the old parts because they had different tolerances, but we were confident that we had re-established what was important to the function. And we were able to use testing to prove that we'd got margin against failure for durations multiples of the planned life of the part. That was a great result for us, but it cost time and money. And there was one hiccup along the way that I'd like to just spend 1 minute on now, and that was acceptance criteria. If you have very clear acceptance criteria, then great. If you don't, then testing can lead to inconclusive results. So we saw wear on a part of the component. We didn't know whether that wear was normal and acceptable or if it was a problem, although we did know that the part had functioned beyond planned life. But it was just an iteration that we had to go through then to understand whether or not that wear was acceptable, and it was a little bit more work, a little bit more time. And the way we got through it was by looking at some ex-service parts and establishing that wear was normal and hadn't undermined the reliability. So here's my summary really of what those 5 examples have told me is important to manage risk, to try and avoid those unexpected consequences. The first key thing is clarity of communication of requirements. It runs through most of the examples. Writing things down in an unambiguous way and supporting that with very clear drawings, sketches, descriptions, face-to-face conversations, really important. The best requirements in the world will only generate good outcomes if they're understood by all the other people, all the other functions that have to deliver them. Secondly, you can never assume that because you've written a requirement, that is what will be delivered. The capability of different special processes, welding, inspection, heat treatment, forging. The designer needs to really understand those capabilities, need to understand the limitations and the risks, and take steps to manage those risks. And that leads on to the third point, really. There is no substitute for going and spending time talking to other disciplines, trying to understand their specialism to a level appropriate to help you understand what they're telling you, and help you work together to manage the risks. And if you do those three things, focus on the clarity of communication, focus on understanding the capability, focus on managing the risks, then you will really go a long way to avoiding those unexpected events that can lead to unintended consequences. So I hope you've enjoyed the webinar, and we'll now open to questions. Okay, we've had time for some questions to come in now. So the first question I've had from Alex is around the first topic, and on the good practice on materials. The question is, for complex structures, the risk mitigation instead of full-scale prototyping could be to use a scaled simulation model, often cost-effective and, depending on the process, relatively accurate. And yes, I would agree with that. As with all of these things, it depends very much on the type of process that you're trying to model. So, if you've got a medium complexity system that you can scale down relatively easily, and you can accurately represent the heat masses and the heat losses and the process equipment in a scaled way, then that's obviously the right thing to do. And we always have to try and balance off cost, program, and quality. So a really good approach using a scaled model. What I would say though is that in some cases, I have found that a full-scale model, even if it's only a partial representation of the final component, but a full-scale model that allows you to use full-scale heating elements and cooling elements, for example, is really invaluable, because you've got the right sort of heat masses, you're using the actual equipment that you're going to use on the job, and I have seen trials throw up some unintended results that we've then been able to refine the process to make sure that the actual heat treatment went well. Okay, and another question on the sort of grades of material that tend to be more susceptible to heat treatment. This is a really broad topic. I will declare that I'm not a materials engineer. However, I think where you've got a transition weld in particular, that's a real risk point. And often we'll join, austenitics and low alloy steels together, and heat treatment at high temperature can release some of the elements of the mix, depending on what it is. So perhaps some carbon, which can migrate to the bond line. And with a transition weld in particular, one of the things you're trying to avoid is reducing the properties in either the bond line between the two metals or the heat affected zone associated with that. So that's one particular risk point. And another is high strength steels used in bolting applications, where so you don't have a transition weld. You've got one material structure, but the strength is a combination of both the composition, the different elements that are mixed together, and the microstructure that's achieved through the heat treatment. And often both the time at temperature to allow different elements to go into solution and form the right size grain structures, and the cooling rates are what are important there. So, go on. Just two simple examples. I don't know whether this will be a discrete topic in one of our future STMG conferences in October, but I do know that IMechE is also running a nuclear materials conference towards the end of the year as well, and so that might be another opportunity to delve more into the sort of challenges and risks with material selection. Okay, a question on NDE, and just to clarify what I mean by qualification. So for the highest integrity regions on different components, we sometimes need to go above and beyond the standard manufacturing inspections that might be required by code. We tend to work to demonstrate that we're compliant with the ASME boiler and pressure vessel code, and that will define sort of defect sizes and orientations for different types of processes. And standard manufacturing inspections developed by PCN qualified inspectors will give us the confidence to claim the standard code reliability. But for some regions, we need to go above and beyond that, and we will specify qualification in those cases. Qualification really means two things. The first is that we write a very detailed technical justification for the capability that's been developed, and we subject that justification to independent scrutiny. So we run a board called the Inspection Qualification Board. It has independent members on it, external to our organisation, and they will challenge the clarity and the robustness of the work that's been done to justify an inspection technique. So that's the first thing that I mean by inspection qualification. The second thing is that as well as making sure that the technique is sound, we will also require that the technique and the individual inspectors who are going to deploy the technique are qualified. And qualification requires that test pieces are manufactured under the control of the IQB with hidden defects, and the inspectors, using the qualified inspection procedure, have got to demonstrate that they can reliably detect and, if necessary, size those hidden defects in that blind test piece without any prior knowledge of what size, orientation and location those defects will be in. So it's the most robust level of substantiation of an inspection that you can imagine, and that, you know, for the inspections that we put through that level of qualification, you know, you can absolutely guarantee to a very, very high level of reliability that if a defect were present, you would find it. Okay, a question on damage allowance, questioning whether it's right to add more material for a low likelihood event. So the low likelihood event obviously being, you know, accidental damage. And it's a good question. I think I said when I was talking to the slides that, you know, it's a compromise. We should take benefit from our modern analytical methods. You know, we can use techniques such as limit load analysis to really refine the thickness of a pressure boundary section, and that's the right thing to do because, you know, it saves money through not having to procure as much material, but the risk is that if damage occurs, and you've gone to the absolute limit, then you've got nowhere left to go, and you end up either replacing the part or doing a lot of extra analysis to try and remove other conservatisms, or perhaps even putting some sort of operational constraint on use of the part, and none of those are particularly palatable. So I think the thing that I would always recommend is that you start with an understanding of, well, what's the risk of damage, and then what's the consequence. So for parts that are very tightly toleranced, that have got to sit inside a valve or a pump, well, clearly you're not going to put an extra damage tolerance allowance on those parts because that would undermine their functional performance. And the risk of accidental damage occurring ought to be relatively low. It ought to be easy to handle those parts, and you're probably making relatively large quantities, so you can accept a certain scrappage rate as long as you plan for it in your factory, and you can deliver reliably to your customer. For very large forgings, though, very long lead time, individually very expensive. A program of work, perhaps to build a new power station, might only order, one or two of a particular type of forging. Although I think it is appropriate to optimise the design, I think you have to be realistic about a forging that's going to spend years going through a factory. Is going to involve difficult handling and lifting operations when it goes to site and is installed in the plant. There are going to be lots of other activities working around it to build the plant around it. Then I think actually in that case it's absolutely worth adding some sort of allowance to account for the unintended. Okay, and then one final question, I think, unless any more pop in. The question of inspection and defining orientations. The example was about being very explicit and understanding capability. The question is, should designers be trained in NDE techniques? Well, I don't think you need to get designers PCN qualified, for example. But I do think that designers ought to have a really good appreciation of NDE techniques and indeed other techniques. So I think they should have a good understanding of material science. I think they should have a good appreciation of welding techniques, inspection techniques. I think they should have a good understanding of how the customer is going to operate the product that they're designing, and make sure that their assumptions about that are valid. And the level to which they need to have that awareness, I guess, will vary, person to person, depending on what they're working on. But I do think it's worth organisations investing in. I'll call it kind of overview or awareness training. So getting a designer to spend a few days or a week, with a welding department, seeing firsthand their challenges and learning something about the techniques, or perhaps attending a structured, welding appreciation course for a couple of days. Likewise with NDE, going and spending time with inspection teams or doing some level of training in NDE, I think is really useful. But training in and of itself has limitations. So if we provide training to people, then I think that is really useful. But inevitably, they'll be trained using the tools and techniques and understanding the capabilities and limitations that apply on the date they're trained. And one of the great things about being a professional engineer is that we all grow and learn and develop through the work that we do and through CPD. And so how do you keep that appreciation fresh? and I think I didn't use this phrase during the presentation, but I think that the phrase I would use is go look see. So I'd always encourage, the designer, and I keep focusing on the designer because it's my background, but I'd always focus on the person setting the requirements. I would always encourage them to go and talk to the other functions, and not just in a meeting room, but actually go and talk to the other functions in their workplace. So if you really want to understand how difficult it is to make the weld on the part that you've designed, well, go and talk to the welder trying to implement the welding technique. If not on your part, at least on something similar, and understand how challenging the thing that you've asked for is. And the same with NDE. Go and spend some time with the NDE engineers and ask them to show you the technique, and show you the responses they're getting on the oscillograph and oscilloscope, and kind of explain what they're looking for, in terms of back wall echo and response from different types of defects, and explain how difficult it is for them to interpret that, and through having regular conversations, going to the shop floor, talking to the experts in different functions, then you will get a good appreciation of what the technology is, and you'll keep it fresh and live. Right, I don't see any more questions. I'm just going to double check, but no more questions. So I guess with that, I will just thank the IMechE for organising this. I'll thank Workcast for hosting, and I'll thank the attendees out there for taking the time to listen to me. I hope it's been informative. And final reminder, conferences to look out for later in the year. Thank you very much, and enjoy the rest of your day. Bye now.